I've been looking at these bearded dragons, they're amazing. I mean, look at these, they're cuddling. Oh my God, they're so cute. Look, he's like nibbling it. Oh my, it's got wings. It's got wings, it's got wings, it's got wings. Oh, these are amazing. Oh, look, he's cuddling. Oh, he's licking his mate. He's licking his mate. Oh, he loves that. Insect. Oh. OMG. It's so cute. It's so cute. Look, it's a shark. It's a shark. Oh, I want it. I want it now. Oh. You will not believe this. There is a dog on the corridor. It's so cute. So fluffy I could die. So, and have a look at my cat this weekend. It's amazing. Look, I'll show you the pictures. Like, so he's been. Well, this is him on the Christmas tree at Christmas. We haven't pulled it down yet. Look, he loves it. Look.
Yeah,
And on this one, look, let me show you this one. This one is eating his dinner. Look how cute he is. Look, he's like playing with it. Look, there's a video. I'll show you this video.
I hate them. Okay, let's look at example 1 then. So we're going to use a Venn diagram to help us answer these questions on probability. I've already drawn the Venn diagram, and as you can see I've drawn a box around the outside. That's really important. So this question is all about cats and dogs, so let's label one of our circles C for cat and D for dog. Now with Venn diagram questions you should always start right in the middle, and that is going to correspond to the last piece of information. So 2 people like both cats and dogs, so that is going to go in the overlap. So I'm going to put 2 there. Now we know that 5 people like dogs, but that doesn't mean they necessarily only like dogs. So we've already counted 2 of them here. So if we want 5 in total, we've already counted 2. That means we must have 3 left that are in this section. These are the people who only like dogs. In a similar way, we know 7 people in total like cats, but we've already counted 2 of them, the 2 who like both cats and dogs. So that means there must be 5 more who only like cats. Well, we know there are 30 members of staff in total. We've already counted 10 of them. So on the outside, there must be 20 people who don't fit into any of these categories. And so that's it. That's the Venn diagram done. So now we're in a position to be able to answer the questions. So part B says, what is the probability that Dr. Young is paired with a teacher who does not like cats? So we want to find the probability that they do not like cats. Well, all the people who like cats are in this circle here. So we want to count up all the rest of them. So it's these 3 people, these 20 people, and so in total that is 23 out of 30. And that's that one done. So part C says, what is the probability Dr. Young is paired with a teacher who does not like cats or dogs? Now this is where the English, when we write the sentence in English, is a bit ambiguous. Okay? What this means is we want to look for the probability that I am paired with the teacher who does not like cats and does not like dogs. So we want to look outside of this circle because they don't like cats, but they also don't like dogs, so they can't be in any of these circles. So actually we're looking for these people here. These are the people who don't like cats and don't like dogs, and so that's 20 out of 30, which cancels down to 2/3. That's that example finished.
Do you know they had that climate change conference in France and stuff, and there's loads of wars and stuff. Do you know what I hate? I hate bearded dragons. I hate how scaly they are. I hate the way their little neck flaps. Who keeps a lizard for a pet? What a nonsense animal. Who eats it? It doesn't even add to the food chain. Ridiculous. Bearded dragons.
Right, so in example 2 we now have 3 categories. So we have cats, and we have dogs, and we have bearded dragons. So just like the last example, we're going to start with the very middle. So that's the people who like dogs, cats and bearded dragons. So the answer to that is 7. We put that right in the middle. They're the people who like all 3. So now the next piece of information up says 11 like dogs and bearded dragons. But that already includes the 7 we've already counted. So when we look at the overlap just between dogs and bearded dragons, that's here. Well, we know 11 like both. That's this bit here. We've already included these 7. And so to make it up to 11, we just put 4 there. So we've done that one. So now let's look at cats and bearded dragons. Well, that's this section here. We've already included 7 of them, so now we want to say how many only like those things and not dogs as well. If we want there to be 10, we've got 7 of them, and so that must mean there must be 3 more. Finally, dogs and cats. Well, that's this section here. We want 15 in total. We've already got 7. 15 minus 7 leaves you with 8. Right, so now we're on to the one animal only. So we want 40 like bearded dragons. Well, this circle contains the people who like bearded dragons. But this means they don't only have to like bearded dragons, so we've already counted these numbers. And so in total, we've already got 4 add 7 is 11, add 3 is 14. We want to make it up to 40, so we must have another 26 in here. We've got 53 like cats. Well, that's this circle. We want this whole circle to equal 53. 8 add 7 is 15. Add 3 is 18. We need to make it up to 53, so that leaves another 35. And finally 25 like dogs, so that needs to be the total in this whole circle. Well, we've already got 8 and 7 is 15. Add 4 is 19, so we need 6 more. What we mustn't forget is the outside, the people who don't fit into any of these categories. Well, we know there are 100 members of staff in total, so if we were to add all these numbers up, we get that it's 89, so that means there must be 11 people who don't like any of them at all. So that's part A done. So now let's look at the questions that we can use, that we can now solve using this Venn diagram. So we want, what is the probability that an extra member of staff likes dogs only? Well, if we look in the section that is only dogs, then we're looking at here. Well, there's only this bit of the Venn diagram where they like dogs only. These sections, they like another animal as well. So therefore, it must be 6 out of the total number of members of staff. So that's 6 out of 100, which cancels down to 3 over 50. Right, part C. Does not like bearded dragons. Well, for this one, we want to look at everything that's outside this circle if they don't like bearded dragons. So that's this, add this, add this, add this. Well, if you add that up, 35 add 8 is 43, add 6 is 49, add 11 is 60. So that's 60 out of 100, which cancels down to 3/5. Right, part D. This is another one where the way you would write it down in English doesn't necessarily match up with how we'd write it down mathematically. So it says, does not like dogs, cats or bearded dragons. So that's the same as saying we want to find the probability that they do not like cats and do not like dogs and do not like bearded dragons. Well, If they don't like any of them, they must be on the outside here. And so the probability is just 11 out of 100. Right, the final question has the word given in bold. So we're told some information here. We're told that they definitely like dogs. And so I'm going to put in red the people who like dogs. And so because we're told they definitely like dogs, then we're no longer looking out of 100. We're only looking out of the people who like dogs. And so our probability is actually going to be out of 25. And we want to say, given that they like dogs, so given we're looking out of these 25 people, find the probability that they like dogs and cats. So we already know they like dogs. What's the probability they also like? Cats. Well, we're looking here. This is the bit where they like dogs and cats. It's in this section here, and so it is 15 out of 25.
So we're going to look at some formal notation we can use with Venn diagrams. First I want to set up my Venn diagram, and this time I've got two events involved, and we usually put an S on the outside as a set of everything. And we're going to have two events this time, and we're going to call them A and B. A might be liking dogs, and B might be liking cats. It could be anything. So we're going to go through a general kind of look at things. So this, if I set up my Venn diagram again, making sure I always put my S, my A and B, this says A intersection B, and we commonly use and instead of intersection. Okay? So the area where A and B are. And we can see this, that the area in here where we've got both A and B is this middle section here. Now I'll show you a great method of showing this, is that I'm going to colour in A, but hatching one way, and then I'm colouring B with hatching the other way. And you can see why they'd use the word intersection. So where they intersect here, this bit is A and B. So if I get rid of these bits, which I'll use in a moment, what I'm left with is A intersection B, A and B. Okay, let's do another one. And we've got a different symbol this time. A, B, don't forget that S there. This time we've got A union B. We commonly use the word or, so we'll have someone where it's A or B. And you could probably guess that A or B is at any of these two areas here. But we could look at this hatching method again, and we could say, okay, well, let's hatch A this way. Let's hatch B the other way. Okay, we see I've got A intersection B in the middle, but everything that's coloured B is A or B. It's anywhere that way. It could be A, or it could be B, or it could be both. Okay, so this whole area that's shaded is A or B. So if I want to make these really clear, I could just shade them in a bit clearer, that all these areas are what I'm after. Okay? This little bit of notation here is not A. So if I draw my Venn diagram again, I've got A and B, and there's our S again, and A is this bit here. So not A, it's just everywhere outside of it. So I have to be very careful. Okay, and I've just gone over a little bit there. I don't want that bit, I want everywhere that's not in A. Okay, so this means not A. Okay, and as we just go across to the other part of the board, we can see we've got some more complicated problems. So here, this says not A, intersection B. Well, let's use that shading method, that hatching method. So well, let's colour in A, well, not A, with one hatching. Okay, so I want to do that. So this bit is not A. So be careful to avoid going anywhere in that A circle. You can go in the B circle, that's fine, but don't slip into the A circle. We've got some good hatching. I've done that. Okay, and then I said, let's do B in the opposite direction of hatching. So B, Put anywhere in the circle of B. Good. Right, okay. So the bit that I'm after is the bit that's intersection. So both of them. So it's where they're both coloured in. And this seems to be this like kind of part of the moon here. This bit's only got a bit of hatching, so I don't need that bit. And then all this bit around the outside, I don't need that bit either. Sometimes what people do is they do that as like a working method, and then underneath maybe say, okay, well, I've worked it out using my working, and I can put A and B again. I can say it was this area here that I was after. So that area there is the intersection of not A and B. Okay. Right, well, let's try another one over here. Okay. So that's not A or not B. Okay. So let's do my hatching method again. So I want to colour in not A, and it's very similar to the first example. And it'd be very easy for me to rush this, but I want to take it steady. So not in A. Okay. And then let's colour in not B the other way. Okay. So it's not in B. Make sure I don't go in that B circle. Well, can't do geography if I keep going in those bits there. No corner for me. Okay, so let's have a look at the bit with or. So it's everywhere shaded in, and it seems to be everywhere shaded in, except for this intersection here. So if I was going to say the area which is, could be not A, or could be not B, I'd say it's everywhere except this middle section here. So I could take my time, colour the whole diagram in, have some good shading, and just leave this bit free. Obviously that'll be a lot neater on my exam. Right, okay, now let's go back down here to a slightly harder one. And you can see I've used two Venn diagrams that I've set up already to help me. Because I can't do all this all in one step, I have to do two. So I'm going to look at where A intersection B is, the bit inside the bracket. Well, A intersection B, we saw that earlier. That's the bit in the middle. And I could use my hatching technique to do that. So, not that, I'm looking for anywhere that's not A intersection B, will be all the rest. It's actually the same as what we've got up there. So, shade it in here. In lesson, you'll have a go at some of these questions. In an exam, you'll have to just know which area so you can pick out the probabilities that will be in there when we get to that. Okay? Right. And our last example, quite a tricky one because we've got knots flying around everywhere. We've got a knot there, we've got a knot with the A, and we've got a unit as well. So I'm going to do what I did here. I'm going to go for the bit that's inside the bracket first, not A or B. So I'm going to have to do my hatching method. That's going to be a bit tricky. So let's go for doing hatching for not A. Trying to be neat on this one because I don't want to confuse myself. Okay, so that's definitely not A. I've avoided the A circle. Or B. So I'll do the big hatching. So that's just this bit here. Remember this or symbol or this union, that's going to be everything that's shaded in. So it's everywhere except that bit. Okay? And I can see that, I've done that. It's everywhere that's got some hatching in. Now we want not that. So we want not that shading, we want the other bit. I kind of like the negative in a photo. So I want this bit here. Okay? That was the bit that I'm after. Now if you get good at these, you'll be able to answer the questions on probability really easily.
Okay, so Mr. Newton's just been talking to us about how we can model the different scenarios in a Venn diagram using the set notation, using the letters to represent the events. So for example, this circle here in this Venn diagram represents the event liking dogs. But obviously Dr. Young was talking about the questions specifically asking about the probability of events. Now actually that's not a big issue because we can use these probability, P, and brackets, and then we can use the letters like we did in set notation to represent the probabilities. Alright? If that sounds confusing, I think you'll see it's not too difficult when we look at the questions. So if we look at this first question that Dr. Young did, it was the probability that we do not like cats. Alright, well the way I would rewrite that is I would say it's the probability of not cats. So that's also commonly called C complement. It's the complement to liking cats, the alternative. Alright, that was straightforward enough. Let's have a little look at part C. So part C is the probability that the teacher does not like cats and does not like dogs. Well, when we rewrite that, that would be the probability of C complement, not C, doesn't like cats, and D complement, not D, doesn't like dogs. So that's the probability, doesn't like cats and doesn't like dogs. And that was example 1 sorted. I hope you can see it saves a lot of space. Now when we get to example 2 and we go through, well, these are slightly, ever so slightly trickier. Just have to be a little bit careful when you write them. So in words, part B was probability likes dogs only. Well, when we think about that, that's the probability of them liking D, but in this circle D we've got people who like cats, like bearded dragons, hell, they even like all 3. Well, we only care about the ones that like dogs only. So it's the probability of D as we've written, and not being C, not liking cats, and not being B, not liking bearded dragons. Alright, so this is the probability that they like dogs only. Probably they like D and C complement and B complement. Alright, and obviously it doesn't change the answer at all, it's just our notation. Alright, part C is the probability that they do not like bearded dragons. Well, this is a nice straightforward one because we don't care whether or not they like cats, dogs, or nothing. All we care about is that they don't like bearded dragons. So all we have to write for this is the probability of not B. Probability of B complement. Anyone that falls into that category does not like bearded dragons. And I'm going to write it again over here just in case that wasn't clear. Probability of not B. Okay, and part D. Part D was does not like dogs, cats, or bearded dragons. Well, these fussy people, they would be written like this. So that's the probability of not cats and not dogs, and unsurprisingly, not bearded dragons. And that's how we write. And I hope you can see that's far, far, far simpler than writing out that whole bracket. So it's really useful when we can use this notation. Alright, so I'm going to talk to you very quickly about the addition rule. And now, you saw with Mr. Newton already the probability of A or B. And using his hatching method, you saw that it was anywhere shaded before. Now we also have this rule, probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Now I'm going to sort of talk you through why that works. Because if we look at here, we've already agreed that everywhere that's shaded is either A or B. And this is useful because we only need to know any 3 bits of information and we can work out the missing piece by rearranging. So let's look at it. If I say probability of A or B, well, if I do the hatching bit by bit, that's going to give me, over here, I can say, well, that's the probability of A. That's covered that, the probability of A, plus the probability of B. That's this bit over here. So I've got the probability of B. But then we have a small issue, because we just said the probability of A plus the probability of B. We've actually sort of done an overestimate in the building trade, because they've counted something twice. You can see this bit we've shaded in the middle, the intersection. Well, we've got the hatching going in both directions. So we've actually counted some of our value twice. So this bit here has been counted twice. You can see the hatching goes both ways. By counting the probability of A plus the probability of B, we've counted it twice. So all we need to do is take away one lot of that middle value. And we've already seen from the explanation before that this is the probability of A and B. So if we take away one lot of the probability of A and B, That'll leave us, well, that leaves us with the probability of A or B. But now it's not overlapping. And so by doing this formula, you've got the exact value of probability of A or B. And what's kind of nice about this is I already said we actually can find out any one of these probabilities by rearranging. This is one of the two most common ways, with the subject being probability of A or B. The other common way that you see it is when you have probability of A and B as the subject, because that's the two times it's used most commonly. So that's easy enough to see if you rearrange. I could add the probability of A and B to both sides. So I've got probability A and B. Add that to both sides, that leaves me the probability of A or B plus the probability of A and B equals probability of A plus the probability of B. All good. And now to make probability of A and B the subject, we're just going to take away probability of A or B from both sides. And so by taking away both, we're just left with the probability of A and B on the left, and on the right that equals the probability of A plus the probability of B minus the probability of A or B. So it works both way rounds. You can have either one as the subject. Bonza. Okay, so example 3. This is an example of how one of the ways we can use this addition rule. So we've been told that A and B are two events, and we know that the probability of A is 0.6, the probability of B happening is 0.7, and we know that the probability of A or B is equal to 0.9. So then in part A it asks us to find the probability of A and B. And using our addition rule, we can see that the probability of A and B is equal to the probability of A plus the probability of B. Take away this probability of A or B. So we know the probability of A is 0.6. We know the probability of B is 0.7. And we know the probability of A or B is 0.9. So that gives us with the probability of A and B occurring, both happening, is 0.4. Alright, so that's part A. Now part B asks us for this probability of A complement. Now, if this wasn't already obvious, I would hope that you remember, dredge up from your mind from GCSE, that the sum of all possible events, either happening or not happening, is going to equal 1. 1 is certain. So the easiest way to find the probability of A complement, A not happening, is to take 1 and take away the probability of A occurring. So that's going to be 1 minus 0.6, which coincidentally is also 0.4. Now, to tackle parts C and D, we have enough information now that we can actually draw ourselves a little quick sketch of a Venn diagram. So if I draw my space, my little S, and I've got event A and event B, and when I've got the information like this, it's usually easiest to start from the middle and work out. I know the probability of A and B now is 0.4, so that's this bit in the middle. That's where A and B both occur. I know the probability of A is 0.6, so I know that if 0.4 is already accounted for, then this little bit here left over is going to be 0.2 to make it up to 0.6. That's the difference. Similarly, the difference between 0.4 and the probability of B is going to be 0.3, the difference between 0.4 and 0.7. So this will be 0.3. And together, a nice way of checking, we know the probability of A or B is 0.9. And if we add that up, 0.2, 0.6, 0.9. Yeah, that's my probability of A or B. So what's left over? Well, that must be 0.1. So that's the probability of neither A complement and B complement. Alright, so what does part C actually ask us for? Well, part C asks us for the probability of A complement or B. The probability of not A or B. Well, now that I have my little diagram drawn, I can do my hatching to work out the answer. So the probability of not A, I'm going to carefully draw that because that's everywhere that's not inside this circle. So I'm going to draw that going this way. And I'll draw that like so. And this bit's not A. This is not A. This is not A. Not A. Not A. Not A. Not A. Or the probability of B. So going this way, I'm going to do my probability of B. And this is probability of B. It's probability of this bit inside here. It's maybe A, but it's certainly also B. So that bit's going there as well. Now, the probability of not A or B, well, when it's or, it's anywhere that's shaded. So for C, we've got the probability of not A or B is going to equal all three of these parts that we've shaded in. So that's 0.4 plus 0.3 plus 0.1. So that's 0.7, 0.8. So that is my probability of not A or B. Alright, for D, well, this is the probability of not A and B. So for this bit, we want the bit where it overlaps, crisscrosses. If you see in your little diagram, that's this bit here. And we can see straight away, straight from what we've already worked out, that's just 0.3.
What have you missed out, Doug?
I think who does not like and does not like dogs. I think it's meant to say cats there.
Oh, yeah.
I don't know what this is all about either. Who?
Who?
Oops. That's clearly a bit for the outtakes, isn't it?
Do you know, with global warming and stuff, and you know, wars and horrific things, do you know what I really hate? I hate bearded dragons. I can't do it.